Silchar will introduce us to the professor today.
Okay. Thank you, Tiranga, for this privilege. So let me introduce to you all to Professor Vashisth. So Professor Vashisth did his BTech in civil engineering from IIT BHU in 2012, followed by MS in 2014 and PhD in 2018 from Penn State University. Further, he did his postdoc from Texas A&M. He joined University of Washington as an assistant professor in January 2021. This month. So his areas of interest lies in the interdisciplinary research on the interface of mechanics and material science. So broadly, his areas of research comprises of advanced composites, molecular mechanics, rapid manufacturing, bio-inspired composites, etc. Notably, during his PhD, he developed an accelerated reactive atomistic simulation that can simulate reactive kinetics for high barrier energy reactions, which has been commercially incorporated in software such as LAMPS and SCM ADF. So also he has two provisional patents on his work on targeted heating for multimaterial bonding using radio frequency fields. So over to you, Professor Vashisht.
Thanks, Sankosh, and thank you so much for inviting me for this talk. I really apologize for the last week technical difficulties that I was having. We just moved to Seattle. We're just trying to figure out everything here. So there were like some technical difficulties, and there was a thunderstorm rolling over the city. So thank you so much, and let me share my screen. Perfect. Can you guys see my PPT?
Yeah, Professor.
Okay, perfect. So what I'll do today is I'll just like as Ankush also mentioned that I've worked in a bunch of different areas with the overarching theme of advanced toughened composites. So what I'll do today is show you a little bit of what I did for molecular dynamics, for toughened composites, and for rapid manufacturing. So that's kind of my thought. I won't get into like the nitty gritties of how I did, what I did, and exactly the small details. But I'll give you an overarching idea as to what I do and what my future lab uh, plans to do. So I'll start off with this very nice schematic. This is probably the schematic that I use for all my presentations. It's a schematic showing the relative importance of different materials over the course of human history. It is from Michael Ashby's book, Michael Ashby of the famous Ashby plots. And if you can see here, I don't know if you guys can actually see my mouse or not, the cursor or not. Um, but if you see the polymer composites and ceramics, pretty much over the course of my lifespan, their relative importance has got shot up tremendously, and this is mainly because their application in aerospace industries, automobiles, and even in common household applications. Polymers, composites, and ceramics are basically becoming an essential part of our everyday routine. And I'm really fortunate to be working in these three areas, or my focus is on these three different types of materials. Uh, and interestingly, he calls that we are living in the age of molecular engineering, where if we can change the molecular structure of the material, we can basically achieve whatever our end application or end goal or end character for these different types of materials. So I'll show you how I basically touch upon or how I'm able to leverage the molecular structure, or how I'm able to tailor the molecular structure or study the molecular structure to see how a particular type of polymer or ceramic or composite behaves. So in general, kind of uh, the center of gravity, or the centroid of my research, is mechanics of materials. So I look at different types of materials and study the mechanics of those materials. So I've done a bunch of fiber composite processing and characterization during my PhD. So I basically looked at out of plane impact on fiber composites. So that was something that I spent like over 4 years working on. The project that kind of got me excited to work in composites was bio-inspired composites. So you can actually see here, there's a actuating composite that can change its shape and stiffness depending upon how much internal pressure you're putting in the composite. I've also worked on polymer-derived ceramics. So these are basically polymers that you cook at really high temperature and they turn into ceramics. And they have a very interesting behavior. The smaller they get, the stronger they get. Um, Another area of interest for me is additive manufacturing of thermosets and ceramics. So mainly doing some sort of with free-form additive manufacturing of thermosets. Rapid manufacturing is something that I'll talk about today. How we use radio frequency waves to rapidly heat and cure thermosets or composites. And finally, reactive molecular dynamics, where we are able to look at the molecular characteristics using simulations. So to uh, to basically explain my area of expertise or like my skill set, I think this is a really nice diagram which kind of captures everything. So I do some simulations, experiments, modeling, and these are like closely knit with the areas of interest that I have, which is lightweight composites, molecular dynamics, and smart or rapid manufacturing. So overall, my focus is to basically couple experiments and simulations to understand a particular type or understand the mechanics of a material. So what I'll do is like I'll touch upon like one area or like one project from each of these circles that I've shown you. So I'll start with lightweight composites. Uh, Sorry, I'll start with the reactive molecular dynamics. Sorry, I cheated. I'll start with the reactive molecular dynamics. I'll go to lightweight composites and then talk about rapid manufacturing. So reactive molecular dynamics or REACT-FF, I was really fortunate to work with one of the co-inventors of this method. He was my PhD co-advisor. And atomic simulations are really good in a way because they can provide you very nice insights into the performance of different fillers or polymer matrices or whatever material you're trying to use. If you have a wealth of material, if you have hundreds of materials and you have to channel down to 4 or 5 materials, this is an excellent way to do that. So, so the motivation or the framework that I developed, it's called accelerated REACT-FF. So I'll tell you the motivation. The motivation was that we found a bunch of papers where if you look at epoxy is made up of two parts. There's a curing agent and there's epoxide molecule. When these two molecules come together, they basically make the epoxy. So your aeroplane parts are made up of thermostating epoxies. And what happens is that these reactive sites, this NH2 and this epoxide, they react with each other. They cross-link with each other. Now, till now, what has been done is that the way people run the simulations, they say that once these two sites are within a certain distance from each other, the molecules basically cross-link. So they say that if this NH2 and this epoxide are within 10 angstrom from each other, they cross-link with each other. Well, that's not exactly true. The way a reaction works is like, the molecules basically they come together. There's a pathway to the reaction. So what we did is we call it accelerated REACT-FF or accelerated reactive molecular dynamic simulations. We say that the first step to the simulation is that this distance criteria need to be fulfilled. We say that, okay, like the amine and the epoxide need to be within a certain distance from each other. But after that, we give these molecules a push to go over the transition state. So if you look at the reaction coordinates, your reactants are here, you give your reactants a little bit of energy. So the way it happens is like you put your epoxy in an oven, you heat it, and when you take it out, it's cured. So the like when you heat your epoxy, you're basically giving this extra energy to your epoxy to go over the transition state and make products. So we do exactly the same in simulations. We give them a little bit of extra energy to get to the transition state, and then it's completely up to the molecule if it tumbles back down to the reactants or if it goes to make a product. So basically, like when these two criteria are fulfilled and it's a nice pathway, we get a reaction. So this is how the reaction looks like. So you see the distance criteria is fulfilled, and there's a really good pathway, and the energy that we gave it was good enough for it to react. And you see that the two molecules react with each other. So that's basically, the beauty of accelerated reacts FF is that it weeds out all the unwanted reactions. That there might be some reactions where the epoxide and the amine might be in a very weird orientation, and they might not actually react with each other. So in that case, like you would never get a reaction with this method. So why is it useful? So let's say you have a bunch of epoxides, bunch of amines, and you need to figure out that, okay, I need a modulus of 4 GP or something, and I have these thousands of epoxides and amines. How do I figure out which one would give me a particular modulus, a particular range of temperature where these epoxides can work? That's where simulations are really powerful. So let's say you want to find the modulus, you want to find the TG, coefficient of thermal expansion, density, atomic oxygen impact. You can do that with simulations. If you make a large enough system, I just showed you a reaction of two molecules, but if you make a really large enough system, you can do virtual mechanical testing that you see here on the left. You can do stuff like atomic oxygen impact. So for example, if you want to look at what type of epoxy coating might be good for a lower Earth orbit satellite, and you want to study the atomic oxygen impact on different types of epoxies, and you want to figure out if a linear molecular chain would be nice or like a cycloaliphatic type of chain will be nice, what should be the molecular structure of your polymer that you put on a satellite. This is a really powerful tool. So moving on, I'll talk next about lightweight toughened fiber composites. And the motivation here was this work was basically done in collaboration with NASA and Army Research Lab here at Penn State, where I was pursuing my PhD. And the thought was that helicopters, they have or the motivation was that helicopters have these drive shafts. They basically transmit the torque from the engine to the rotors. So basically, that's how your rotors rotate and your helicopter flies. And these drive shafts are kind of like the Achilles heel of the helicopter. So if there's an out of plane impact, if there's if somebody shoots at these drive shafts, they can basically rupture completely, and the helicopter would be a dead weight and drop down. At the same time, so there is a need to make these materials ballistically tolerant. But at the same time, you need to make these structures very light as well. So you need to transition from metals to fiber composites, but you need to be also aware of the fact that when you make these fiber composite drive shafts, they need to be ballistically tolerant. So the type of damage that you have in these composites, it's delamination, some fiber breakage, micro cracking, matrix cracking. So our thought was to improve the matrix performance in order to basically improve the impact tolerance of the material. So this is what we did. We thought that we'll add nanofillers to the matrix. So any fiber composite has two parts. You're looking at the cross section here. There's the carbon fiber and there's matrix. The matrix could be thermosetting polymer or a thermoplastic polymer. We were specifically interested in thermosets. So we wanted a nanofiller that can actually get between the carbon fibers. It does not agglomerate. It stays well dispersed. It's easy to make. So we actually went with low aspect ratio nanosilica particles. So these particles had a diameter of 142 nanometers. So these were like really, really small particles. So you can actually see these particles here on the right. These small particles have a size of 142 nanometer. So how does these nanoparticles improve the the toughness of the material? There are two ways. So basically, to improve the toughness of the material, the crack should dissipate more energy. So the first method that we kind of used, or basically the nanosilica particles employ, it's called crack deflection. So instead of the crack traveling in a straight line, it actually deflects a lot. So instead of traveling a length of L, the final length actually, since it's wavy, it's doing this wavy nature, it ends up being longer than L. So you're able to dissipate more energy. The other method is particle pullout. So here again, since the particle is not able to travel in a straight line, and there's energy that is dissipating in pulling out this particle from the matrix, there's more energy dissipated as the fracture propagates or the crack propagates. So we designed miniature drive shafts, miniature helicopter drive shafts. So this is kind of a setup that I came up with. Took me a really long time to come up with this setup, and this is where I feel this is where the Indian skills of coming up with jugaad helped me a lot. So this is a machine called filament winder. So here you can see that it's filament winder. If you think about it, it's like a 3D printer that prints on a cylindrical bed. So there's like fiber, there's a cylindrical bed. So if you think about a bottle as a, I don't know if you can actually see my face or like my camera, but if you think about a bottle, you're actually making structure on a bottle surface or a cylindrical mantle that you see here. And I had to come up with like different ways to heat up the bath. So this was really interesting. I really enjoyed it. It was really challenging. It took me almost 3 to 4 months to figure out the setup. But as I said earlier, I was able to use my Indian skills of jugaad to come up with this whole setup. So here is how the testing procedure looked like. We had these small helicopter drive shafts that I made. So we did normal ballistic impact. So what that means is there was a bullet that went through the diameter of the tubes. This testing was done at NASA. Then we did pulse thermography to look at the damage in the tubes. This part of the work was done at the Army Research Lab, and the torsion testing of these impacted tubes was carried out at Penn State. And in kind of like the whole wealth of data that we generated, it took a couple of years to get to this point, but it could be actually summed up in this one graph, where you see that the total damage area is on the x-axis, and the residual shear strength is on the vertical axis. So the residual shear strength is the strength of these tubes after a ballistic impact. And you can see that as the damage area is increasing, the strength of the material is going down. And what we found was that two concentrations that work the best for our systems was 25 and 15 weight% of nanosilica in this particular type of curing agent called DDS. So it was really good because DDS is like the type of material that is used in thermosets also. It gives a really high TG, or glass transition temperature. That's the temperature where a material transitions from glassy to a rubbery state. So this actually turned out to be really good, that DDS resin actually showed the best performance. Here you can see the fracture surface for a fiber composite. You can see single particles hanging out, which result from particle pullout. This is the carbon fiber. This is the direction of the crack. Um, so overall, we were able to conclude that addition of nanosilica did improve the post-impact strength of these miniature drive shafts. Just a fun fact about the last thing, we made life-size drive shafts eventually, and we actually tested like 3 feet long drive shafts finally. So that was really fun. Finally, I'll talk a little bit about targeted heating using radio frequency. This is basically a very interesting method for rapid manufacturing, out of oven rapid manufacturing of composites. So the main idea here is that you take capacitor electrodes and you basically simulate them, or you input a radio frequency or RF power into them. And RF is basically the same wavelengths that your phone works at. So we usually work around 1 to 100 megahertz of frequency. And what happens is that, if you have this blob of material that has this correct conductivity, it's a very sweet spot, that like if you have this particular conductivity for a material, what happens is that the material heats rapidly. So here you can see that on this animation that we added 5-8% of graphite, and this is not even graphene, this is graphite, to simple epoxy, and we hit it with just 5 watts of RF power, and it heats really rapidly. Within a couple of seconds, it's able to get to 60 degrees Celsius. So this was a very, very interesting discovery made in the Green Lab in 2018. That's pretty much when I just entered the lab as a postdoc, and started to brainstorm, like, where else can we apply this technology. So what I did, one of the projects that I worked on, our thought was to make continuous manufacturing of prepregs using radio frequency waves. And prepregs are like the materials that are used for making aerospace composites. So when you make an airplane wing, you actually don't dip the carbon fiber in epoxy and put the carbon fiber on an aerospace tool in the actual facility. The dipping of carbon fiber and the partial curing of the carbon fiber is already done in a previous facility. When you make aeroplane, you basically take these prepregs and you stack them up, and you basically consolidate and cook them. And basically that's what the Boeing company does. So before that, a company like Toray, what they might do is they might make these prepregs. So the way they make the prepregs right now is they have these carbon fibers, they dip it in a matrix, and they heat it in a large oven. So thermosets, when they start curing, they start with 0% of, let's say they start with 0% of cross-linking. Once they achieve, let's say 30 to 40% of cross-linking in the oven, they're actually kind of not exactly bagged, but they're trapped between polyethylene films. And these films are later on released, and you have the prepreg, you lay them up, and you make a composite. So we propose that instead of heating these carbon fiber composites in really large ovens, which are very expensive to operate, we'll heat them using RF field applicators. Like these are much smaller applicators. So it's a very, very easy, very less energy expensive out of oven method for making prepregs for continuous manufacturing. So this is how it would work, or we figured out it would work. That if you have these composite, you pass feeds through the composites, and basically the carbon fibers start heating, and you have more or less like a volumetric heating type of mechanism where the whole volume or the cross section of your composite heats up rapidly. So what we saw was that by varying the amount of input power, just by changing varying the amount of input power, you can get up to like 250 degrees Celsius within 2 minutes. So this was really, really fast. This is like really rapid for rapid curing for epoxies. So this was really good. This was really promising, and this is something that my lab plans to pursue in future as well. So I think with that, I'll just leave it there. I kind of gave you a little bit of taste of reactive molecular dynamics, toughened composites, advanced manufacturing, and if you think about it, basically, like the plan of my lab is to work at these different scales. Like we envision to work at these different scales, starting from molecular dynamics to actual structural composites, and understand, try to extract and understand like what we can from each and every scale, and how that can help, or how basically how each and every scale helps us to understand the physics of the material. So there are some other research projects that I've working on. So I'll just give you like a quick 20-second elevator pitch for all of these other projects. So one of them is mechanical size effect of ceramic fibers. So if you know Griffith theory, it says that the strength of a material is inversely proportional to the square root of the size of the flaw that that material has. So we actually started making really small ceramic nanofibers, and we found that it doesn't follow Griffith theory. Their strength increases really rapidly as you decrease the temperature, and then comes a point where they have no flaw in them, and basically they become flawless fibers, and they reach the limit strength of the material itself. So this is a very interesting project. I worked on stability of MaxEne. This is something that I'm still working on with some collaborators. MaxEne it's a new type of nanomaterial, just like graphene. It's called MaxEne. It has layers of metal and carbon or nitrogen that are sandwiched between each other. So it's a very, very interesting, very novel, and very rapidly increasing material in the research community. Another area that I've been working on, it's called laser-induced graphene. So it's a very interesting material. You basically shoot a laser on a polymer, and you make graphene. So it's a one-step process to make graphene. Some people don't think it's a graphene. I also doubt if it's exactly graphene, but it's a very interesting material. Another method is another thing that I've been working on is wire melt electrospinning of thermoplastics. I mentioned earlier that I've been working on freeform additive manufacturing of thermosets and ceramics, and some work on fracture surfaces of nanocomposites, trying to understand the toughening mechanisms in nanocomposite fracture surfaces using nanomechanics and data science along with experiments. So that's pretty much it. Thank you so much for your patience, and I'll be more than happy to answer any questions that you have. All right.
Thank you, Professor Vashisth. It was a great presentation, and I would just like the attendees to ask any questions if you have to Professor Vashisth.
Hello, Professor Vashisth. This is Navneet here. Very intriguing presentation. I'm really motivated by your talk. So I had a couple of questions.
Hmm.
So firstly, my question is related to the Reax FF, I mean numerical method that you showed in your sort of initial slides. So I
Hmm.
just wanted to know how is a Reax FF method or simulation is different from a traditional molecular dynamics simulation.
Yeah. The nice thing about as the name suggests, the reactor molecular dynamics, it can actually simulate reactive events. So if you look at the energy, so if you look at the energy equation, so these are both like all most of the molecular dynamics systems. Most of the molecular dynamic simulations are basically energy based. So they have like bunch of uh, if you look at it, if you look at the equation, they have like bunch of components, for angles, dihedrals, lone pairs, etc., etc. So the nice thing about reactor molecular dynamics is that it has like it assumes a continuous curve for the bond order. So it doesn't say that the bond order is 1, 2, or 3, or 4. Like there's a continuous curve for it. So basically, you're able to get the transition state, and you're able to see the reactions of different types of reactive events. It's really good for uh, low activation energy, or low when you have values of when this EA value is like very low. It's really good for those type of reactive events. So for example, like when you're looking at explosion of RDX, or conversion of graphene from polymer to graphene. So it's really good for those type of events, but it becomes like really challenging when the EA, or the activation energy, becomes like really large. So for example, like 40 kcal per mole. So that was kind of the motivation of coming up with accelerated reacts of it. Because there, we are inputting extra energy just in the reactive sites. Um, so I don't know if that exactly answers your question or not.
Yeah, yeah, yeah. So, and then adding a side question to that only. So, since we are trying to investigate interactions among, polymer chains. So,
Mhm.
is it possible to predict sort of some, mechanics aspects like stress strain curves or something like that?
Yeah,
So, sort of
yeah, yeah.
continuum scale things. Yeah.
Yeah, exactly. So that's exactly what we did here. I just had the animation here, but we did calculate the modulus of the polymer as a function of strain rate. So polymers, their performance is dependent on the strain rate of the materials. So we looked at different strain rates of the polymers, and then tried to figure out like how the polymer reacts to different varying strain rate. So yeah, you
Oh,
can actually get like stress strain curves for polymers,
okay.
depending
And
how
then,
well depending how well your force field is strained. So the basically the material properties for these atoms and angles, it's called force field. Just like you put material properties in finite element, it's in reactive or in molecular dynamics in general, it's called force field. And those force fields are generally trained using first principle calculations or DFT methods. So you need to make sure that when you train those force fields, it is trained in a way that it can capture the modulus, or the stress strain curves, or the stress strain behavior of the material as well.
okay, and so I was really excited by the sort of scale bridging thing that you showed. Going from a nanoscale to a sort of a continuum scale or a macro scale. So a question in this regard is that a polymer at a nanoscale may behave very differently from that at the bulk level. So
Yeah,
how is that being taken care of? So that was one of my questions that sort of I'm very curious to know about.
that's really good, because that's one of the questions for my research lab also. So
Yeah,
so that's
yeah.
something that we are we are trying to look at we are trying to look at in my lab as well. Especially like for the work that I did, what I tried to do is that. But in general, what I did was that I had some inputs from molecular scale, and I had bulk data, and I tried to correlate them how that goes. Then I had some micromechanical models, and I tried to correlate them with the laminar level properties that I measured for carbon fiber epoxy composites. And then the measured properties that I had at the laminar level, I had a bunch of experiments from like structural composites. So I used like simple classical laminate plate theory or simple models to analyze how well these two basically like correlate to each other. So, but again, the entropy increases. Like it's when you're going from scales, like the error increases as you climb every scale, and that's one of the areas of interest that I have, and I feel that this is where you can use data science very cleverly or very nicely to uh, try to decrease that error when you climb each level.
Okay, thank you so much. And
Yeah, that was a very nice question. Yeah.
Thank you so much. And one final question. So I was asking a lot of questions. Yeah. One last question. So in slide 13, you showed sort of for the toughened composite work, this one, yeah, slide 13, you showed these two prevalent mechanisms, crack deflection and particle pullout. So I mean, these mechanisms or these theories, so how did you, I mean, cement that these were the dominant mechanisms? Where did you complement this with some simulations, or where there's some visualizations or experimental validation for that?
Yeah. So I guess maybe I missed this, but if I don't know how clear this is, but I had multiple SEM images for this. But if you can see here, you can actually see like particles being pulled out, just like remaining on this side of the surface. So particle pullout is like you see that like very easily. Crack deflection, we also saw that on some other SEM images, but like the main mechanism that we saw was particle pullout, and you can see that a lot like here. Like you can actually see like particles basically sticking out or making craters on the epoxy a lot. So yeah, we used SEM to do that. Another thing that I'm doing right now, I have a graduate student who is working on this right now. Is um, he's using basically a combination of nanomechanics, data science, and data science, and experiments to figure out like how much one of the mechanism happens, like how much uh, particle pullout you have, and how much crack deflection you have. So that's also very interesting.
Yeah. Thank you so much. Yeah.
Yeah, no worries. Thanks.
Any more questions?
Sir, a very good evening to you, sir. This is Danish Khandekar from second year mechanical engineering. Sir,
Hello.
hello, sir. Sir, your presentation was really interesting, and it got me like very much intrigued. So, sir, my
That's good.
question is rather a broad-based question. So, like, I just wanted to ask that how long will it take? Like you are in US and doing research, and I mean all developing all these technologies. But I just wanted to ask how long will it take India to to indigenously develop this all these technologies? Because I have seen the application of all these composites and all in various aircrafts. Specifically the huge aircrafts the US Air Force used to make, that ones. I mean,
I think there's every place has its own strength, and if you look at I remember this, like one of the few like initial papers that I read for my PhD when I started was from the Rubber Institute at IIT Kharagpur, So every place has their own strength. US strength is the strength, like US is like, of course, like, they have a really good capital also. So their strength is manufacturing and analysis as well. But if you look at India as well, like, there are like some exceptional professors at specifically at IIT Kharagpur, IIT Kanpur, who have done like tremendous work in composite analysis and even composite fabrication as well. So there's it's one of those things, like it's like stuff is like a little bit hidden here and there. Like you just have to look for it. And I tell this to a lot of people that when I started, I even when I was doing my undergrad, like I did not know about the Rubber Institute at IIT Kharagpur. This is like one institute that I'm stressing about because like now I read their papers like on a regular basis. But there are like places, there are like so many places in India which do like cutting edge research. So it happens everywhere. Like it's happening everywhere. It's just that we have to like look really carefully, like what is happening, where is happening. So yeah, I don't know if that answers your question, but that's kind of like my personal view on this.
Sir, I really like the way you like you included the term jugaad in this presentation, which is basically the Indian way of doing everything. So
Yeah,
that is the thing.
yeah,
Thank you,
yeah,
sir.
yeah.
Thank you, Danish, for the question. Any more question? Uh, Professor
Hello,
Vashisth,
sir.
okay. Go ahead.
Sir, my name is Yugabret Gogoi. I'm from second year. Sir, you have introduced us to a term magazine, which is quite new for me. So, can you just explain how magazine is different from graphene, like its advantages over graphene, if it
Sure,
has
sure,
any?
sure. Yeah, it's very interesting. You caught that, and that's very good. Maxine, it was discovered in 2011 by the Yuri Gogotsky group in Drexel University in Philadelphia, and uh, Maxine basically, graphene is just a single layer of carbon. So what Maxine is that it has a layer of metal, carbon, metal, carbon, metal, carbon, metal, carbon, and depending like how much layers you want. So think about it like a metal, two metal layers sandwiching a carbon layer. So the
Okay.
nice thing about this material is that you have a layer of carbon, so you have nice properties of uh, kind of have properties of graphene, but at the same time you have properties of metal also because you have a top layer of metal. So you can have really good like conductivity. Uh, the nice thing about Maxines is that apart from this titanium, carbon titanium layer, is that you have surface functionality also. So there's some functionality or some surface groups also. So that could be like fluorine, OH, oxygen, and there's like so many, like if you think about it, it's there are like so many small knobs that you can turn to change the properties of graphene. In graphene, you basically have a layer of graphene. If you add oxygen to it or OH to it, you make the best you can do with graphene is like make graphene oxide or something. But
Okay.
Maxine, like you can change titanium to chromium, you can change carbon to nitrogen, you can change the surface functionality. So you can change the modulus from right now. We know that you can change the modulus from around 300 GPa to almost like 1 terapascal, and you can change the electrical conductivity of the material. So these are like they have like it's just like so many knobs you can turn, and you can have like so many different applications. So it's a very exciting material. The kind of the Achilles heel for this material is that it's not stable at room temperature. It basically
Okay.
disintegrates. So it's think about it like, aluminum, like, when you keep if you have aluminum surface, like you develop a layer of aluminum oxide. So similarly, like, vaccines are also like reactive at room temperature. You can't just like keep them uh, keep them uh, keep them on the outside. Like graphene, you can put graphene on a table, come back 5 years later, it'll be mostly graphene. Vaccine, if you do that, like, it disintegrates. So that's a very interesting area of future research where like I plan to work in.
Okay, so like in which temperature it will be stable, like the range?
So that's the tricky thing. Like, it can actually start to disintegrate or degrade at room temperature also. It can start reacting with the oxygen and the water that is present in the atmosphere at room temperature also. So it's like the stability. It's a very interesting question because, like, you can change the material chemistry and some might degrade really fast as compared to the others. So it's a very, very open question. It's a very uh, I don't have a correct answer, like a specific number for like when for the range that will be stable in. So
Uh, okay, thank you, sir.
yeah.
Any more questions?
Excuse me, sir.
Hello.
Hello, sir. Am I audible?
Yes.
Yeah, go ahead.
Hello, sir. This is Tejaswini from second year mechanical. So my question is, from the laser techniques which you have mentioned, or even from the Reacts FF, can we develop the amount of energy needed to dissociate an ionic bond, sir, such as NaCl?
Um, Not sure about that. I believe you're talking about like these laser-induced graphenes. Uh, I'm not sure if people have actually lased ionic bond or like materials like this. It works like specifically for this type of material. It works really well for polymers because polymers, they have like covalent bond, they have a lot of carbon, and they have these six-ring members with the sp2 carbon. So what happens is that, when you pulse them with laser, like very high power laser, these six-ring molecules, five or seven-ring molecules, they start to rearrange to form a graphitic structure. That's kind of the mechanism that a polymer turns into a graphitic type of material. But I'm personally not aware of like any like lasing any like material with ionic bonds to make any material. So sorry about that. Like I don't know too much about like lasing ionic materials.
No issue, sir. Thank you, sir.
Any more questions, guys? Or I mean, oh, okay. Professor Vashisth, I have a question. Is there any specific polymer? You that can be used for laser-induced graphene, or any polymer can be converted to graphene if you shoot laser on it.
So there's a bunch of polymers that have shown to work for laser-induced graphene. The only difference is like how much laser power you put in,
Okay.
or like how you shoot the laser. So you might have to defocus the laser a little bit, and you might need to increase or decrease the power of the laser here and there. But apart from that, like, they've actually made laser-induced graphene out of coconut. So I guess everything is possible for these type of materials. So as long as you have like a carbonous type of structure. So they were able to so I think coconut has like cellulose, I believe, like the outer shell is made up of cellulose. I'm not completely sure. but they were able to make like laser-induced graphene or leg out of that also. So that was pretty interesting and pretty impressive.
Yeah, thank you. Thank you. Any more questions, guys?
Good evening, sir. Am I audible?
Hello. Yep.
Good evening, sir. So I have a doubt. So you mentioned about the targeted heating in that slide. So I was thinking about this. Sir, you showed that it was a very efficient process. So you achieved very high temperature in very small time with that radio frequency. So is that process having some defect, some drawbacks on the properties of the material after that?
Yeah, so that's a excellent question. That's something that my first PhD student will be doing. So that's kind of the thought process that the thought is like this is a completely different way of manufacturing or curing something. So yeah, that's a wonderful question. So I don't know the answer, but maybe like in a couple of years I will. So.
Thank you, sir.
Any questions? Okay.
Well, this has been like really nice. I really appreciate. I think the type of questions that you guys ask, like I don't think as a second year or a third year, even a fourth year student, I would have been able to ask those questions. I think I was like really busy playing football and cricket at that time. So really nice. It's a very very good initiative by ASME NIT Silchar that you have these type of talks. I think this is excellent. Maybe the silver lining in this uh, this Corona, this era of Corona. But this is really nice. This is really good that you have these type of talks, and you're able to learn so much about so many different types of things that is not covered by the curriculum, but you're able to get this type of exposure. So this is excellent. That's really nice. Yep.
Thank you, Professor Vashisth.
Oh, wonderful.
Thank you, sir.
Okay. So I guess we'll keep it there and take care, everyone, and hopefully talk to you guys soon in some capacity.
Thank you, Professor.
Okay.
Thank you, sir.
Okay.
Thank you.
Take care.
Thank
Bye-bye.
Bye.
Bye. Bye.